Imagine the most violent collision in the entire universe, not a car crash, not meteors slamming together, not even stars exploding. Imagine two black holes, each with the mass of dozens of suns, spinning around each other at half the speed of light, getting closer and closer until they finally merge together in a cosmic catastrophe so violent it literally shakes the fabric of space-time itself. This is real. This happens. And when it does, the energy released in a fraction of a second exceeds the light output of all the stars in the observable universe combined. For that brief moment, this collision is the brightest thing happening in the entire cosmos, except you can't see it with your eyes because it's not light being released. It's gravitational waves, ripples in space-time itself, spreading outward at the speed of light, carrying the news that two monsters just became one. Tonight, I want to take you through what actually happens when two black holes collide. Not the simplified version, not the glossed over version, but the real, detailed, step-by-step process from the moment two black holes begin their death spiral to the moment they merge into a single, larger black hole. I want you to understand the physics, the violence, the beauty, and the profound implications of these cosmic collisions. Because when you truly grasp what's happening during a black hole merger, when you understand the scales of energy and the warping of space-time involved, it changes how you see the universe. It makes you realize that the cosmos is far more dynamic, far more violent, and far more beautiful than most people ever imagine. And we're living in the first era of human history where we can actually detect these events, where we can hear the space-time ripples arriving at Earth from collisions that happened billions of years ago and billions of light years away. That's extraordinary. That's profound. That's what I want you to understand tonight. So let's begin this journey. Let's watch two black holes collide. Let's see what happens to space-time when the universe's most extreme objects meet in the most violent collision possible. Before we can understand what happens when black holes collide, we need to be clear about what black holes actually are, because there's a lot of confusion and misconception. A black hole is not a hole. It's not empty space. It's not a vacuum cleaner sucking everything in. It's an object, a real physical object with mass. But it's unlike any other object in the universe because its gravity has become so extreme that it's changed the fundamental nature of space-time around it. Let me explain this carefully. Every object with mass warps space-time. You do, I do, the Earth does, the Sun does. This warping of space-time is what we experience as gravity. When you stand on Earth, you're not being pulled down by some mysterious force. You're standing in warped space-time. The Earth's mass has curved the space-time around it, and you're following the straightest possible path through that curved space-time, which happens to be toward the Earth's center. This is what Einstein's general relativity teaches us. Gravity is geometry. But for most objects, the warping is slight. Earth curves space-time just a tiny bit. The Sun curves it more, but still not dramatically. But a black hole curves space-time so severely that it creates what we call an event horizon. This is a boundary, a point of no return, beyond which the warping of space-time is so extreme that all paths lead inward. If you cross the event horizon, there is no escape, not because something is pulling you, but because the geometry of space-time itself has been twisted such that every direction you could possibly move leads toward the center. It's like being on a hill that's so steep in all directions that no matter which way you try to walk, you're walking downhill toward the bottom. Except this isn't a hill in space, it's a warping of space-time itself. Inside the event horizon, all future paths lead to the singularity at the center, and at the singularity, our equations break down. We think it's a point of infinite density, but that's probably where quantum mechanics needs to step in, and we don't have a complete theory of quantum gravity yet. For our purposes, what matters is the event horizon. That's the boundary that defines the black hole. That's the surface of no return. And nothing, not even light, can escape from inside it. That's why we call them black. Not because they're made of some black material, but because they don't emit or reflect light. They're invisible. The only way we can detect them is by their effects on things around them, by how they warp space-time, by how they affect the motion of nearby objects, by how they bend light passing near them. Black holes form when massive stars collapse. When a star at least about 20 times the mass of the Sun runs out of nuclear fuel, its core collapses under its own gravity. If the core is massive enough, nothing can stop the collapse, not even the quantum pressure that holds up neutron stars. The core collapses to a point, creating a singularity and an event horizon. A black hole is born, and once created, black holes are remarkably simple objects. They have mass, they might have spin, they might have electric charge, though that's rare, and that's it. Everything else about them is determined by those properties. The size of the event horizon is determined by the mass. For a black hole with the mass of the Sun, the event horizon would be about 3 kilometers in radius. For a black hole with 10 times the Sun's mass, the radius is about 30 kilometers. The radius scales directly with mass. So stellar mass black holes, the kind formed from collapsing stars, have event horizons that are just a few to a few hundred kilometers in radius. They're tiny compared to stars, but they contain the mass of many suns compressed into a region smaller than a city. The density is incomprehensible, and the gravity near the event horizon is so strong that tidal forces would tear apart any normal object. This is what we're dealing with when we talk about black hole collisions. Two of these objects, each with the mass of dozens of suns, each with gravity so extreme that space-time is twisted into a point of no return, coming together, meeting, merging. Let's see how this happens. Black holes don't just randomly collide. They have to start somewhere, and that somewhere is usually a binary star system. Imagine two massive stars born close together, orbiting each other. Over millions of years, they live their lives, burning through their nuclear fuel. Eventually, one reaches the end of its life and collapses into a black hole. Then, later, the other does the same. Now you have two black holes orbiting each other, a binary black hole system. At this point, they might be separated by distances similar to the distances between stars in binary systems. Maybe a few times the distance from Earth to the Sun, maybe much farther, and they're orbiting each other, going around their common center of mass, just like the stars did before them. But something is different now, something that wasn't important when they were stars, but becomes crucial now. They're radiating gravitational waves. Gravitational waves are ripples in space-time caused by accelerating masses. Any accelerating mass produces them, but they're incredibly weak for most situations. The Earth orbiting the Sun produces gravitational waves, but they're so feeble that they have essentially no effect. But black holes orbiting each other are different. They have enormous mass, and they're accelerating as they orbit, constantly changing direction. This acceleration produces gravitational waves, and while even for black holes, the effect is initially small, it's not zero. Those gravitational waves carry away energy, not much at first, but some. And as energy leaves the system through gravitational radiation, the orbit changes. The two black holes draw closer together. This is called orbital decay. It's the same principle that causes satellites in low Earth orbit to gradually descend and eventually burn up, except there it's atmospheric drag removing energy. Here it's gravitational wave radiation, and as the black holes get closer, something interesting happens. The closer they are, the faster they orbit each other. The faster they orbit, the more strongly they accelerate. The more they accelerate, the more gravitational wave energy they radiate. The more energy they radiate, the faster they draw together. It's a feedback loop. The process accelerates. What might take billions of years when they're far apart takes millions of years when they're closer, thousands of years when they're even closer, years when they're very close, and seconds in the final moments. This is the inspiral, the death spiral. Two black holes circling each other, getting closer and closer, speeding up as they go, radiating gravitational waves that grow stronger and stronger, until finally they merge, and we can observe this. We can detect the gravitational waves from the final moments of the inspiral and the merger itself. This is what LIGO does, but let me take you through it step by step so you understand what's actually happening as these black holes spiral toward their doom. Let's start when they're moderately close, maybe a few thousand kilometers apart. At this point, they're already orbiting each other incredibly fast. They're going around each other hundreds of times per second. Each black hole is a tiny object, just a few dozen kilometers across at the event horizon, and they're whipping around each other at speeds that are a significant fraction of the speed of light, maybe 10% of light speed, maybe more. And they're radiating gravitational waves continuously. The gravitational waves at this stage are like a siren that's slowly increasing in pitch. The frequency is related to the orbital frequency. As they orbit faster, the frequency of the gravitational waves increases. This is called the chirp. It starts low and rises, and as it rises, the amplitude, the strength of the waves also increases. Because the black holes are getting closer and the violent motion is becoming more extreme, if you could somehow convert these gravitational waves to sound, which scientists have done for visualization purposes, you'd hear a chirp, a rising tone that goes from a low rumble to a high-pitched peak. It's the sound of space-time itself being shaken by the most violent dance in the cosmos. Now, as they continue to spiral inward, the speeds increase. The black holes are now orbiting each other thousands of times per second. They're so close that the distance between them is just a few hundred kilometers. And they're moving at 30, 40, 50% of the speed of light. Imagine that. Objects with dozens of solar masses whipping around each other at half the speed of light. The energy involved is staggering. And all of this energy, some of it is being radiated away as gravitational waves. These waves are spreading outward at the speed of light, carrying the news of this cosmic catastrophe to the universe. And if Earth is in the path of these waves, billions of years and billions of light years later, we can detect them. We can measure the tiny stretching and squeezing of space-time as the waves pass through. But let's stay focused on the black holes themselves. As they get even closer, something remarkable happens. The event horizons themselves start to deform. Remember, the event horizon is not a physical surface. It's a boundary in space-time, but it has a shape. And that shape is determined by the space-time geometry. For a solitary, non-rotating black hole, the event horizon is a perfect sphere. But when two black holes get very close, their presence distorts each other's space-time so much that the event horizons become elongated. They start to stretch toward each other. Imagine two water droplets approaching on a surface. Before they touch, they start to bulge toward each other. The black hole event horizons do something similar, except this isn't surface tension. This is space-time geometry responding to the presence of two massive objects in close proximity. The black holes are now so close that the distance between their centers is just a few times the radius of their event horizons. Maybe they're 60 kilometers apart, and each event horizon is 20 kilometers in radius. At this point, they're orbiting each other tens of thousands of times per second. The speeds are approaching the speed of light, 70%, 80%. The gravitational waves being emitted are incredibly strong. The power being radiated is unimaginable. In the final moments before merger, the power in gravitational waves exceeds the power of all the light from all the stars in the observable universe combined. Think about that. There are about 2 trillion galaxies in the observable universe. Each galaxy has hundreds of billions of stars. All those stars are shining constantly. The total light output is enormous beyond comprehension. But for a brief moment, these two black holes, through gravitational waves alone, are putting out more power than all of that light combined. This is the most energetic event that occurs in the universe, except for the Big Bang itself. And it's happening in a region of space just a few hundred kilometers across. The energy density is incomprehensible. Now we reach the final second. The black holes are so close that they're moving at 95, 98, 99% of the speed of light. They're orbiting each other hundreds of thousands of times per second. The gravitational waves have increased in frequency and amplitude to a peak. The chirp is screaming, and then the event horizons touch. This is the merger, the moment when two separate black holes become one. What happens at this instant is difficult to describe because the mathematics becomes extremely complex. The space-time geometry is so warped, so dynamic, that you need the full machinery of general relativity to describe it. And even then, you need supercomputers to solve the equations numerically because there's no simple analytical solution. But here's what we understand. When the event horizons touch, they don't bounce off each other. They can't. They merge. They form a common horizon. And very quickly, within a fraction of a second, this common horizon settles down into a new, larger event horizon. The two black holes have become one. But the new black hole is not calm. It's oscillating. It's vibrating. It's shaped not like a perfect sphere, but like a distorted, wobbling blob. This is called the ring-down phase. The merged black hole is ringing like a bell that's been struck. It's oscillating, sending out gravitational waves as it does. But these waves are different from the inspiral waves. The ring-down waves decay. They get weaker and weaker as the black hole settles into its final stable configuration. Within a few milliseconds, the oscillations have damped out, the gravitational waves have faded, and what remains is a single, stable, rotating black hole. The collision is over, the merger is complete, and the universe is left with one black hole instead of two. But this new black hole is interesting. It has less mass than you might expect. If the two original black holes had, say, 30 solar masses each, you might think the merged black hole would have 60 solar masses. But it doesn't. It might have only 58 solar masses. What happened to the missing 2 solar masses? They were converted to energy and radiated away as gravitational waves. Einstein's famous equation, E equals mc squared, tells us that mass and energy are equivalent. During the merger, some of the mass of the black holes was converted to pure energy in the form of gravitational waves. 2 solar masses worth of energy. That's about 4 times 10 to the 47 joules. To put this in perspective, the Sun's total energy output over its entire 10 billion year lifetime is about 10 to the 44 joules. The black hole merger released about 1,000 times more energy than the Sun will produce in its entire life, in a fraction of a second. That's the scale we're dealing with. That's the violence. That's the power of a black hole collision. And this energy has propagated outward as ripples in space-time, traveling at the speed of light, stretching and squeezing space itself as it passes through, until billions of years later it reaches Earth and we detect it with LIGO. Now, let me help you visualize what an observer would experience if they could somehow watch this collision. Though, of course, in reality, you couldn't survive being close enough to see anything, and black holes don't emit light, so you wouldn't see them directly anyway. But imagine you had some magical ability to observe without being destroyed. What would you perceive? From far away, you'd see 2 black holes, as dark regions where no stars shine behind them. They'd be blocking the light from background stars, and those dark regions would be moving around each other, getting closer and closer. As they orbit, the light from stars behind them would be bent by gravitational lensing. You'd see distorted, multiple images of background stars being warped around the black holes. As the black holes speed up and get closer, this lensing would become more dramatic. The images would swirl and distort more violently, and then, suddenly, the 2 dark regions would merge into one. There might be a flash of light if there was any material around the black holes, matter falling in during the merger. But if the black holes are isolated in empty space with no nearby stars or gas, the merger would be visually dark. The only signal would be gravitational waves, invisible ripples in space-time that you couldn't see or feel unless you had instruments sensitive enough to detect them. From the perspective of space-time itself, though, something incredible is happening. Imagine space-time as a fabric, though this is just an analogy. The two black holes are like heavy weights on this fabric, creating deep wells. As they spiral together, these wells circle each other, creating ripples that spread outward. As they get closer, the ripples get stronger and more frequent, and when they merge, there's a violent shaking of the fabric. The two wells merge into one deeper well, and that new well wobbles and settles. The ripples from this event spread outward through the universe, carrying energy and information about what happened. And here's something profound. These gravitational waves travel at the speed of light, but nothing can stop them. They pass through matter as if it weren't there. They pass through stars, through planets, through you and me. When a gravitational wave from a black hole merger passes through Earth, it stretches and squeezes space itself. It changes the distance between objects by a tiny, tiny amount. We're talking about changes smaller than the width of a proton over distances of kilometers. But these changes are real. Space-time itself is oscillating, and LIGO can measure these oscillations. That's how we know these mergers are happening. We can't see black holes colliding, but we can feel the space-time ripples they produce. We can measure the stretching and squeezing. We can extract information from the waveform about what masses collided, how far away it was, whether the black holes were spinning. All of this information is encoded in the gravitational wave signal. It's remarkable. It's beautiful. It's one of the most profound achievements in the history of science. We're listening to the universe in a completely new way. Before gravitational wave astronomy, we could only observe the universe through electromagnetic radiation, light in all its forms. Radio waves, infrared, visible light, ultraviolet, X-rays, gamma rays. These are all photons, particles of light with different energies. And for most of the universe's history, that was our only window. But black hole mergers don't produce photons. They're electromagnetically silent unless there's material around them. So, for all of human history, until 2015, we were deaf to these events. We knew they should happen based on the theory, but we'd never detected one. Then, on September 14th, 2015, everything changed. LIGO detected gravitational waves from a black hole merger for the first time. The signal was labeled G914, GW for gravitational waves, and the date. This was a collision of two black holes with about 29 and 36 solar masses, about 1.3 billion light-years away. The gravitational waves from this event traveled through space for 1.3 billion years. They passed through countless galaxies, through voids, through clusters of stars, and they reached Earth on that day in September. And for the first time, humanity heard the sound of space-time ringing. The chirp lasted about a fifth of a second. It swept from 35 Hz to 250 Hz, and then it faded, the ring down, the new black hole settling into its final state. This detection changed everything. It confirmed that gravitational waves exist, something that had been predicted by Einstein 100 years earlier but never directly observed. It confirmed that binary black holes exist and merge. It opened a new window on the universe. Since then, LIGO and its partner observatories have detected dozens of black hole mergers. We're now in the era of gravitational wave astronomy. We're routinely observing these cosmic collisions. We're learning about black hole populations, about how often mergers happen, about the range of masses involved. Let me take you deeper into the physics of what's happening during the merger, because there are some subtle and profound things going on that deserve attention. During the inspiral, when the two black holes are orbiting each other but haven't merged yet, each black hole is moving through space-time that's being warped by the other black hole. This creates interesting effects. One is called frame dragging. A spinning black hole, and most black holes do spin because they form from collapsing stars that were rotating, drags space-time around with it. Imagine space-time as honey and the black hole as a spinning ball in the honey. The honey near the ball is dragged around by the spinning motion. This is what a spinning black hole does to space-time. It twists it. And when you have two spinning black holes orbiting each other, the space-time geometry becomes incredibly complex. Each black hole is moving through space-time twisted by the other, and both are spinning and dragging space-time themselves. The resulting geometry is so complicated that only supercomputers can calculate it. But this complexity has observable effects. The gravitational waves emitted depend on the spins of the black holes. If the spins are aligned with the orbital motion, the waveform looks different than if the spins are misaligned or anti-aligned. By analyzing the gravitational wave signal, we can extract information about how the black holes were spinning. Were they spinning in the same direction as their orbit? Were they spinning in random directions? This tells us about how these binary systems formed. Did they form from two stars that lived and died together, evolving in a binary? Or were they two separate black holes that found each other later, perhaps in a dense star cluster? The spins give us clues. Another fascinating aspect is what happens to the spins during the merger. When two black holes merge, the resulting black hole has a spin that's a combination of the original spins plus the orbital angular momentum. Angular momentum is conserved, so the total spin of the system is preserved. But how it gets distributed into the final black hole depends on the details of the merger. And sometimes, the merger can produce a black hole that's spinning almost at the maximum allowed rate. There's a limit to how fast a black hole can spin, related to its mass and the speed of light. A black hole spinning at this maximum is called an extremal Kerr black hole. We've detected merged black holes with very high spins, suggesting that the merger process can efficiently convert orbital angular momentum into spin. Now, here's something really interesting. During the merger, there can be what's called a kick. Because of asymmetries in the gravitational wave emission, the merged black hole can get a recoil velocity. It's like a rocket. The gravitational waves carry momentum, and by conservation of momentum, the black hole experiences a recoil. For typical mergers, this kick is small, maybe a few hundred kilometers per second. But in special cases, if the spins and masses are arranged just right, the kick can be enormous, thousands of kilometers per second. Fast enough that the black hole could be ejected from its host galaxy. Imagine that, a black hole merger producing so much asymmetry in gravitational wave emission that the resulting black hole gets flung out of the galaxy at escape velocity. This is thought to happen occasionally, and it has implications for the population of black holes in the universe. Some black holes might be wandering through intergalactic space, kicked out by merger recoils. We don't know how common this is, but it's a possibility. These kicked black holes are sometimes called rogue black holes or hypervelocity black holes. They're moving so fast that they'll never return to their home galaxy. They're on a one-way journey into the cosmic voids, and if there are enough of them, they might make up a small fraction of the missing mass in the universe, though this is speculative. The point is, black hole mergers don't just create a new black hole. They can dramatically alter the trajectory of that black hole, sending it flying through space at incredible speeds. And all of this is encoded in the gravitational wave signal. By analyzing the waveform, we can tell if there was a significant kick. We can determine the final mass and spin of the merged black hole. We can estimate how far away the merger occurred. We can even get hints about what else might have been nearby, though this is harder. If there was material around the black holes, like an accretion disk or a companion star, the merger might have disturbed that material, potentially producing electromagnetic radiation that we could detect with traditional telescopes. Most black hole mergers we've detected so far appear to be in isolation with no material around them, so they're electromagnetically silent. We only see them through gravitational waves. But there's hope that eventually we'll detect a merger that also produces light, giving us a multi-messenger observation. This would be incredibly valuable because we could pinpoint the location much more precisely and study the environment around the merger. So far, this hasn't happened for black hole mergers, though it did happen for a neutron-star merger in 2017, which produced both gravitational waves and a gamma-ray burst and other electromagnetic signals. That was a landmark event, but we're still waiting for an electromagnetic counterpart to a black hole merger. It might happen, or it might be that black hole mergers are usually so clean, so isolated that they don't produce light. Time will tell. Let me now talk about the energy scales involved. Because the numbers are so large, they become abstract, and I want to make them concrete. We said that a typical black hole merger converts about 3 to 5% of the total mass into gravitational wave energy. Let's take a specific example. Suppose two black holes of 30 solar masses each merge. That's 60 solar masses total. If 5% is converted to energy, that's 3 solar masses, 3 times the mass of the Sun, converted entirely to energy. Using E equals mc squared, that's about 5 times 10 to the 47 joules. To put this in perspective, the atomic bomb dropped on Hiroshima released about 63 terajoules. That's 6.3 times 10 to the 13th joules. The black hole merger releases about 10 to the 34 times more energy. 10 billion trillion times more energy than the Hiroshima bomb. Or, think of it this way, the sun's total power output is about 4 times 10 to the 26 watts. That's 4 times 10 to the 26 joules per second. The sun has been shining for about 4.6 billion years. That's about 1.5 times 10 to the 17th seconds. Multiply these together, and the sun has emitted about 6 times 10 to the 43 joules in its entire life so far. The black hole merger releases about 10,000 times more energy than the sun has produced in its entire lifetime. In a fraction of a second. That's incomprehensible, but it's real. And this energy doesn't come from nuclear reactions or chemical reactions. It comes from pure mass energy conversion. The mass of the black holes is literally being converted to gravitational wave energy. The merged black hole has less mass than the sum of the original black holes. The missing mass has left the system as gravitational radiation. This is E equals mc squared in its most dramatic form. Now, where does this energy go? It spreads outward as gravitational waves, traveling at the speed of light. As the waves travel, they decrease in amplitude. The energy is spread over an ever larger sphere. By the time the waves reach Earth from a merger billions of light years away, they're incredibly weak. The strain, the fractional change in length, is about 10 to the minus 21 or smaller. That means a change of 1 part in a billion trillion. Over a distance of 4 kilometers, the LIGO arms, the change is about 1/10,000th the diameter of a proton. This is why LIGO is such an incredible feat of engineering. It can measure changes that are unimaginably small, changes that are a billion times smaller than an atom. And it does this by using laser interferometry, an exquisitely sensitive technique that can detect tiny changes in the lengths of the 2 arms of the detector. When a gravitational wave passes through, one arm gets slightly longer, while the other gets slightly shorter. Then they swap. The interferometer detects this change and records the signal. And from that signal, encoded in the pattern of stretching and squeezing, we can extract the story of what happened. We can tell that 2 black holes with certain masses and spins merged a certain distance away. We can recreate the final moments of the inspiral, the merger, and the ringdown. We can hear the universe speaking to us in gravitational waves. This is what makes the detection of black hole collisions so profound. It's not just that we're observing violent events, it's that we're observing space-time itself. We're seeing the dynamic nature of the fabric of the universe. For most of human history, we thought space and time were absolute, fixed, unchanging. But Einstein showed us that's not true. Space-time is dynamic. It can curve, it can ripple, and black hole mergers produce the strongest ripples possible. They're the most violent events in the universe, and they're teaching us about the nature of space-time in ways nothing else can. This is frontier science. This is humanity pushing the boundaries of knowledge, and we're living through it, right now. The first gravitational wave detection was less than 10 years ago. We're in the infancy of this field, and already we've learned so much. We've confirmed that black holes exist, that they merge, that gravitational waves are real, that general relativity holds up even in these extreme conditions. And we've only just begun. The future holds even more discoveries as our detectors get more sensitive and we build new detectors in space that can observe even larger black hole mergers. Let me help you understand why these collisions matter beyond just being impressive displays of cosmic power. Black hole mergers are teaching us things we couldn't learn any other way. They're tests of general relativity in the most extreme conditions imaginable. Einstein's theory of general relativity has been tested many times since he published it in 1915. We've tested it with the orbit of Mercury, which matches the predictions perfectly. We've tested it with light bending around the sun during eclipses. We've tested it with time dilation experiments using atomic clocks. We've tested it with the precession of binary pulsar orbits. Every test has confirmed the theory, but all of these tests have been in relatively weak gravitational fields, even near neutron stars, where gravity is incredibly strong by everyday standards. The warping of spacetime is still modest compared to what happens during a black hole merger. During a black hole merger, spacetime is warped so severely that the geometry itself is dynamic and violent. The curvature is changing rapidly. The gravitational fields are as strong as they can possibly be without forming a singularity. This is the ultimate test of general relativity, and so far, the theory passes with flying colors. Every black hole merger we've detected matches the predictions of general relativity. The waveforms we observe match the numerical simulations based on Einstein's equations. The masses and spins we infer make sense. The energies released are exactly what the theory predicts. There are no surprises, no deviations, no hints that general relativity breaks down even in these extreme conditions. This is remarkable. It tells us that our understanding of gravity, at least on these scales, is correct. But it also tells us something else. It tells us that black holes behave exactly as the theory predicts. They're not exotic objects that violate known physics. They're natural consequences of general relativity. When you have enough mass in a small enough volume, an event horizon forms. A black hole exists, and when two black holes merge, they do so in exactly the way the equations say they should. This is important because for decades, black holes were theoretical objects. We thought they probably existed, but we didn't have direct proof. We had good indirect evidence from X-ray binaries and from the motions of stars at the centers of galaxies. But we'd never seen black holes in action, never observed them doing something that only black holes could do. The detection of gravitational waves from black hole mergers changed that. Now we have direct evidence that black holes exist, that they're as massive as we thought, and that they behave exactly as predicted. This is a triumph for theoretical physics. It shows that we can use mathematics to predict the behavior of objects we've never directly observed and be right. That's extraordinary. That's the power of physics. But black hole mergers are teaching us more than just confirming general relativity. They're telling us about the population of black holes in the universe. Before LIGO, we knew about stellar mass black holes primarily from X-ray binaries. These are systems where a black hole is pulling material off a companion star. The infalling material forms an accretion disk and heats up, emitting X-rays. We can detect these X-rays and infer the presence of a black hole. But this method has limitations. It only works if the black hole has a companion star and if material is actively falling in. If the black hole is isolated, or if the companion isn't close enough to be stripped, we can't detect it this way. So our sample of known black holes was biased. We only knew about the ones that happened to be in detectable binary systems. But LIGO detects black hole mergers regardless of whether there's material around them. In fact, most of the mergers we've detected appear to be clean, with no surrounding material. This gives us an unbiased sample of black holes. And what we've learned is surprising. The black holes we've detected through gravitational waves are often more massive than the black holes we knew about from X-ray binaries. Many of the black holes in detected mergers have masses of 20, 30, even 50 solar masses or more. Some mergers involve black holes with masses around 100 solar masses, which is much heavier than we expected from stellar collapse models. This has led to new questions. Are these very massive black holes formed through stellar collapse or through some other mechanism? Could they be intermediate mass black holes formed through successive mergers? Are there gaps in the mass distribution, or is it continuous? We're still figuring this out. But the point is, gravitational wave detections are revealing a population of black holes we didn't know about before. And this is changing our understanding of stellar evolution, of how massive stars live and die, and of how black holes form and grow. There's also the question of black hole spins. By analyzing the gravitational wave signals, we can infer whether the black holes were spinning and how their spins were oriented relative to the orbital plane. This gives us clues about the formation history of the binary system. If the spins are aligned with the orbit, it suggests the black holes formed together from a binary star system and evolved in place. If the spins are misaligned, it suggests the black holes formed separately and later found each other, perhaps in a dense star cluster where gravitational interactions brought them together. So far, we've seen both types. Some mergers have aligned spins, some have misaligned spins. This tells us that there are multiple pathways for forming binary black holes. Some form from binary stars, some form through dynamical interactions in clusters, and the relative frequency of these pathways is something we're still working out. As we detect more and more mergers, we're building up statistics that will eventually tell us how common each formation channel is. All of this is information we couldn't get any other way. X-ray binaries can tell us about black holes that have companions, but they can't tell us about the much larger population of isolated black holes, or about black holes in binaries that don't have active accretion. Gravitational wave detections fill in these gaps. They give us a more complete picture of the black hole population. And as LIGO and its partner detectors get more sensitive, and as new detectors come online, we'll detect more and more mergers. We'll see mergers at greater distances. We'll see mergers involving different mass ranges. We'll build up a comprehensive understanding of black holes across the universe. Now, let me address something you might be wondering. Are these collisions dangerous? Could a black hole merger affect Earth? The short answer is no. We're perfectly safe. All of the black hole mergers we've detected so far have been billions of light years away. The nearest one, detected to date, was about 300 million light years away, which is still incredibly far. And even if a black hole merger happened much closer, the gravitational waves themselves are harmless. They stretch and squeeze space by tiny amounts, but this doesn't hurt anything. When a gravitational wave passes through you, your body is stretched and squeezed by a fraction of an atomic diameter. You don't feel it. It doesn't damage your cells. It's completely harmless. The only way you'd be in danger from a black hole merger is if you were very close to the black holes themselves. Within a few hundred or thousand light years, the radiation from an accretion disk, if there was one, might be harmful. Within a few light years, the tidal forces from the black holes themselves could be disruptive, but we're talking about events that are millions or billions of light years away. They pose no threat whatsoever. In fact, there are almost certainly black hole mergers happening in our own galaxy right now, or will happen in the future. But the Milky Way is large, about 100,000 light years across, and black holes are tiny. The chance of being close enough to a merger to be in any danger is essentially zero. You're far more likely to be struck by lightning or hit by a meteor or win the lottery multiple times than to be affected by a black hole merger. So, these cosmic collisions, as violent as they are perfectly safe for us to observe from our comfortable distance. We get to witness the most energetic events in the universe without any risk. And that's a good thing, because these events are teaching us so much. Now, let me take you through what we still don't know, because for all that we've learned, there's still so much mystery. One big question is about the mass gap. There seems to be a gap in the mass distribution of compact objects between about 2 and 5 solar masses. We've found neutron stars up to about 2 solar masses. We've found black holes above about 5 solar masses. But in between, there's a gap. Why? Is this gap real, or is it an observational bias? LIGO has recently detected a few objects that might be in this mass gap, which is exciting, but we still don't fully understand why the gap exists if it does, or what determines whether a collapsing star produces a neutron star or a black hole. Another mystery is about intermediate mass black holes. These are black holes with masses between about 100 and 100,000 solar masses. They're too massive to form from single stellar collapse, but too small to be the supermassive black holes found at galaxy centers. How do they form? Do they form from successive mergers of stellar mass black holes? Do they form from the collapse of very massive stars in the early universe? Do they form in dense star clusters through runaway collisions? We don't know. LIGO has detected hints of intermediate mass black holes in some mergers, which is exciting, but we need more data. And there's the question of how often black hole mergers happen. We've detected dozens so far, but that's just a tiny fraction of all the mergers occurring in the universe. Most are too far away for us to detect with current technology. As our detectors improve, we'll detect more. But extrapolating from what we've seen to estimate the total rate of mergers across the universe involves uncertainties. We think there might be hundreds of thousands of black hole mergers happening every year in the observable universe, but the exact number depends on how black holes form, how often they end up in binaries, and how quickly those binaries merge. These are active areas of research, and then there's the question of what happens to the merged black hole afterward. Does it stay in its host galaxy? Does it get kicked out by the recoil? Does it eventually merge with other black holes? Does it accrete material and grow? Does it influence the evolution of its host galaxy? These are all interesting questions that we're just beginning to explore. The answers will come as we detect more mergers, as we develop better theoretical models, and as we observe the universe in new ways. Gravitational wave astronomy is still in its infancy. We're like Galileo pointing his telescope at the sky for the first time and seeing moons around Jupiter. We're opening a new window on the universe, and we're seeing things we never saw before. And just as Galileo's telescope led to centuries of discoveries, gravitational wave astronomy will lead to discoveries we can't even imagine yet. We're at the beginning of a revolution in our understanding of the cosmos. Let me help you appreciate the human story behind these discoveries, because science is not just about cold equations and data. It's about people working for decades to achieve something that seems impossible. The story of LIGO is a story of perseverance, of vision, of believing that you can detect something so small it defies imagination. LIGO stands for Laser Interferometer Gravitational Wave Observatory. It's 2 facilities, one in Louisiana and one in Washington State, separated by about 3,000 kilometers. Each facility has 2 arms, each 4 kilometers long, arranged in an L shape. Down each arm, a laser beam travels, bouncing between mirrors. The arms are precisely the same length. When a gravitational wave passes through, one arm gets slightly longer, while the other gets slightly shorter. This creates a tiny difference in the round-trip time for the laser light. By combining the light from both arms, you can detect this difference through interference. But here's the challenge. The changes you're trying to detect are incredibly small. The change in length of a 4-kilometer arm caused by a gravitational wave is about 1/10,000th the diameter of a proton. To put that in perspective, it's like measuring the distance to the nearest star to within the width of a human hair. It's absurd. It shouldn't be possible. And for years, many scientists were skeptical that it could be done. The project started in the 1970s with early prototypes. The full-scale LIGO facilities were built in the 1990s and early 2000s. They ran for years without detecting anything. Critics questioned whether the project was worth the enormous expense. Hundreds of millions of dollars spent, and no results. But the scientists working on LIGO knew what they were doing. They knew the technology needed to improve. They knew that the first-generation detectors probably weren't sensitive enough to detect anything. They needed to upgrade, and they did. Advanced LIGO, a major upgrade that improved the sensitivity by a factor of 10, came online in September 2015, and within days, on September 14th, they detected GWD-0914, the first gravitational wave ever directly detected. Can you imagine that moment? Decades of work, hundreds of millions of dollars spent, careers devoted to building and running these detectors. And then, suddenly, there's a signal, a clear, unmistakable chirp, two black holes merging. The data is so clean, so obvious, that even before they finish analyzing it, they know it's real. That must have been one of the most incredible moments in the history of science. The team spent months checking and rechecking. They wanted to be absolutely sure. They couldn't announce a discovery of this magnitude unless they were certain. And in February 2016, they announced it to the world. Gravitational waves had been detected. Black holes merging had been observed. A new era of astronomy had begun. The announcement made headlines around the world. It was one of the biggest scientific discoveries of the century, and it vindicated decades of hard work by hundreds of people who believed in this project even when others doubted. That's the human side of science. That's what makes these discoveries so profound. They're not just abstract physics. They're the result of human ingenuity, perseverance, and collaboration. The LIGO team includes thousands of scientists and engineers from dozens of institutions around the world. It's a massive collaborative effort, and it's paid off beyond anyone's wildest expectations. Since that first detection, LIGO has detected dozens more mergers. The rate of detections is increasing as the detectors get more sensitive. We're now finding black hole mergers regularly, multiple times per month during observation runs. And each one teaches us something new. Each one adds to our understanding of black holes, of general relativity, of the universe. And the future is even more exciting. There are plans for new detectors. The Virgo detector in Italy is already operating and contributes to localizing sources in the sky. The Kagra detector in Japan is coming online. The LIGO India detector is being planned. With more detectors, we can pinpoint the sources more precisely. We can determine where in the sky the merger occurred. This is important because it allows us to follow up with traditional telescopes. If we know where to look, we can search for electromagnetic counterparts. We can study the host galaxy. We can learn more about the environment where the merger occurred. And there's LISA, the Laser Interferometer Space Antenna. This is a proposed space-based gravitational wave detector that will consist of 3 spacecraft flying in formation, separated by millions of kilometers. LISA will be sensitive to lower frequency gravitational waves than LIGO. This means it can detect more massive black holes merging. Supermassive black holes with millions or billions of solar masses. These mergers occur in the centers of galaxies and produce gravitational waves with periods of hours or days. LIGO can't detect these because its arms are too short. But LISA will be able to. And when LISA launches, probably in the 2030s, it will open yet another window on the universe. We'll be able to observe supermassive black hole mergers across cosmic time. We'll learn about how galaxies evolve, about how supermassive black holes grow, about the history of structure formation in the universe, all from gravitational waves, all from observing space-time itself. This is the future of astronomy, and it's incredibly exciting. let me bring this back to something personal because I want you to understand why this matters to you. You might think that black hole mergers are distant events that have nothing to do with your life. And, in one sense, that's true. They're billions of light years away. They happened billions of years ago. They don't affect your daily life in any practical way. But, in another sense, they're profoundly connected to you. Because understanding black hole mergers is understanding the universe. It's understanding the fundamental nature of space-time, of gravity, of reality itself. And that understanding changes how you see the world. When you know that space-time is not fixed but dynamic, that it can ripple and wave, that it can be stretched and squeezed by massive objects, you see the universe differently. You realize that space and time are not passive backdrops against which events occur. They're active participants. They're part of the story. When you know that black holes exist, that they merge, that they release more energy in a second than all the stars in the universe combined, you appreciate the scale and power of cosmic events. You realize that the universe is far more extreme, far more violent, far more beautiful than everyday experience suggests. And when you know that we can detect these events, that we can measure the ripples in space-time caused by black holes colliding billions of light years away, you appreciate what humanity is capable of. We're not just passive observers of the universe, we're active investigators. We're building instruments that can measure the unmeasurable. We're using mathematics and physics to understand events we can never directly witness. We're listening to the universe in ways our ancestors could never have imagined. That's profound. That's meaningful. That's something to be proud of as a member of the human species. We're part of a civilization that can do this, that can detect gravitational waves, that can understand black holes, that can unravel the mysteries of space-time. And you're living through the beginning of this era. The first gravitational wave detection was less than 10 years ago. You're witnessing the birth of gravitational wave astronomy. You're part of the generation that will see this field mature and flourish. That's something special. That's something worth appreciating. So, when you think about black hole collisions, don't just think about the violence and the energy. Think about what they represent. They represent our ability to understand the universe, our capacity to explore and discover, our drive to push the boundaries of knowledge. They represent the best of what humanity can achieve when we work together toward a common goal. And they remind us that the universe is full of wonders, full of mysteries, full of things we're just beginning to understand. Black hole collisions are not just astronomical events. They're invitations to wonder. They're prompts to think deeply about the nature of reality. They're reminders that we live in a cosmos that's far stranger and more beautiful than we often remember. That's what I want you to take away from this. Not just the facts and the physics, though those are important, but the sense of wonder, the appreciation for human achievement, the understanding that we're part of something larger than ourselves. We're part of a species that can detect space-time ripples from black holes colliding billions of light years away. And that's extraordinary. The population of merging black holes reveals patterns we didn't expect. When LIGO began detecting mergers regularly, astronomers noticed something surprising. The mass distribution isn't what stellar evolution models predicted. Many merging black holes have masses between 20 and 40 solar masses, higher than most black holes detected in X-ray binaries. This presents a puzzle. Standard stellar evolution theory suggests massive stars lose significant mass through stellar winds before they collapse. This should limit the masses of resulting black holes to below about 20 solar masses for most cases. But we're seeing heavier black holes. Lots of them. Several explanations have been proposed. Maybe these black holes formed from stars with lower metallicity. Stars poor in elements heavier than hydrogen and helium. Such stars have weaker stellar winds. They retain more mass, collapse into heavier black holes. This would mean many merging black holes formed in the early universe or in regions with low metallicity. Another possibility involves binary evolution. When two massive stars orbit closely, they can transfer mass between each other. This affects their evolution. Changes when and how they collapse might produce heavier black holes than isolated stars would. Or perhaps some black holes grew through successive mergers. A black hole merges with another. The result is heavier. If that merged black hole later merges again with a third black hole, you get an even heavier object. This hierarchical merging could build up masses exceeding what single stellar collapse produces. Evidence for this comes from observations of black holes with masses around 100 solar masses. These are too heavy for normal stellar collapse. They might be second-generation merger products, black holes that already merged once and are merging again. Detecting these tells us about the merger history, about how black holes grow over cosmic time. The rate of black hole mergers throughout the universe depends on multiple factors. How common are massive stars? How often do they form in binaries close enough to eventually merge? How long does the inspiral take? These questions affect the predicted merger rate. Early estimates before LIGO suggested maybe a few mergers per year detectable by LIGO. The actual rate turned out higher, much higher. During observation runs, LIGO detects multiple mergers per week when operating at peak sensitivity. This implies black hole mergers are common, happening constantly across the universe. Statistical analysis based on LIGO detections suggests tens to hundreds of stellar mass black hole mergers occur per cubic gigaparsec per year. A gigaparsec is about 3 billion light-years. So, in a volume of space 3 billion light-years on a side, dozens to hundreds of black hole mergers happen annually. The observable universe contains vastly more volume. Extrapolating suggests hundreds of thousands of black hole mergers per year across the entire observable universe, maybe more. This abundance tells us binary black holes are a natural outcome of stellar evolution, not rare, not exotic, common, expected, part of the cosmic landscape. Different formation channels produce different observable signatures. Black holes forming from isolated binary stars should have spins aligned with their orbital angular momentum. Because the stars evolved together, their rotations and orbit were aligned from the start. Black holes forming through dynamical capture in dense star clusters should have random spins. Because the black holes formed independently, found each other later through gravitational interactions. Their spins wouldn't be coordinated with the orbit. By measuring spin orientations from gravitational wave signals, we distinguish these scenarios. Some mergers show aligned spins. Others show misaligned or even anti-aligned spins. This indicates both channels operate. Both contribute to the observed population. The relative fraction tells us about where mergers happen. How important are dense star clusters versus isolated binaries? Current data suggests both are significant, but uncertainties remain. More detections will clarify the picture, help us understand which environments produce the most mergers. Eccentricity is another diagnostic. Orbits can be circular or elliptical. Black holes that evolved from binary stars should have nearly circular orbits by the time they reach the frequencies LIGO detects. Years of gravitational wave emission during the inspiral circularize the orbit. But black holes captured dynamically might retain some eccentricity. If two black holes in a dense cluster interact gravitationally and end up in a bound orbit, that orbit might be eccentric initially. If they merge quickly, before the orbit fully circularizes, LIGO might detect residual eccentricity. So far, most detected mergers appear consistent with circular orbits, but there are hints, marginal detections, that might show small eccentricity. These are exciting. They would confirm dynamical formation, prove that some mergers happen in dense environments where black holes find each other through gravitational interactions rather than co-evolving. The distribution of mass ratios, the ratio between the heavier and lighter black hole in a binary, also teaches us about formation. If both black holes have similar masses, the mass ratio is close to 1. If one is much heavier, the ratio is larger. Different formation channels predict different mass ratio distributions. Binary stellar evolution tends to produce similar mass binaries. Because the two stars started with comparable masses and evolved similarly, dynamical formation allows any mass ratio, whatever black holes happen to encounter each other. Observed mass ratios show to preference for near equal masses, but with a tail extending to higher ratios. This supports a mixture of formation channels. Some equal mass mergers from binary evolution, some unequal mass mergers from dynamical encounters. The details constrain models of both processes. Supermassive black hole mergers operate on completely different scales. These involve black holes with millions or billions of solar masses. They reside at galaxy centers. When two galaxies merge, their central black holes eventually sink to the merged galaxy's center. Through dynamical friction, the black holes plow through surrounding stars. Gravitational interactions transfer momentum. The black holes slow down, spiral inward. Eventually they form a binary, and that binary tightens through further interactions with stars and gas, eventually reaching separations where gravitational wave emission takes over, the final in spiral and merger. But the timescales are different. The entire process from galaxy merger to black hole merger can take billions of years. The final in spiral, when gravitational waves dominate, still takes millions of years for supermassive black holes. Because they're so much heavier, their orbital frequencies are much lower. They emit gravitational waves at frequencies too low for LIGO, periods of hours to months. But LISA, the space-based detector planned for the 2030s, will detect these. LISA will observe supermassive black hole mergers across cosmic time. See how galaxies evolved, how black holes grew, how structure formation proceeded. These observations will revolutionize our understanding of galaxy evolution. Because supermassive black holes influence their host galaxies, they emit energy through accretion, create jets, heat surrounding gas, regulate star formation. Understanding how they grow through mergers helps us understand how galaxies evolve. Environmental effects matter for black hole mergers. If a merger happens in a dense gas environment, the gas can interact with the black holes, create accretion disks, emit electromagnetic radiation. This could produce a counterpart signal, something telescopes could detect alongside the gravitational waves. So far, no confirmed electromagnetic counterpart to a black hole merger has been detected. But searches continue. Some mergers might occur in active galactic nuclei, regions where supermassive black holes are actively accreting. Lots of gas and dust. If stellar mass black holes orbit in these disks, they might merge there. The merger would disturb the gas, create flares, potentially detectable. This is speculative but plausible. Similarly, mergers in globular clusters, dense star systems with thousands to millions of stars packed into a small volume, might have weak electromagnetic signatures from surrounding stars or diffuse gas. Detecting such a signature would pinpoint the merger location, allow detailed follow-up. We'd learn about the environment, the host galaxy, the local star formation history, all valuable information, and it would validate multi-messenger astronomy for black holes, just as it was validated for neutron star mergers. Primordial black holes are a speculative possibility. These would be black holes formed in the early universe, not from stellar collapse, but from density fluctuation shortly after the Big Bang. If regions of space were slightly denser, they might have collapsed directly into black holes. These primordial black holes could have any mass, from tiny subatomic masses to thousands of solar masses. If they exist, some might merge, and LIGO might detect these mergers. How would we know if a detected merger involved primordial black holes? Mainly through mass ranges. If we detect a black hole with a mass that's impossible from stellar collapse, below about 3 solar masses or in certain forbidden ranges, it might be primordial. Or if we see merger rates that don't match predictions from stellar populations, primordial black holes might explain the discrepancy. So far, all detected mergers are consistent with stellar origin black holes. But we keep watching. Primordial black holes, if they exist, are candidates for dark matter, the mysterious substance making up most of the universe's mass. If a significant fraction of dark matter is primordial black holes, LIGO might detect them indirectly through merger rates. This is an active area of research and speculation. Testing general relativity continues with each detection. Einstein's theory predicts specific waveforms for black hole mergers, calculated using the equations of general relativity. These predictions are precise, detailed. Every detected merger provides another test. Does the observed waveform match the prediction? So far, yes, always. To within measurement uncertainties, general relativity is correct. But physicists look for deviations. Any difference between observation and prediction would hint at new physics. Modified gravity theories, quantum corrections to general relativity, extra dimensions, all predict slight deviations from standard general relativity. LIGO searches for these deviations in every detection, tests whether gravitational waves travel at the speed of light, whether they're polarized as predicted, whether the post-merger ring-down matches expectations. Every test confirms general relativity. This is both reassuring and slightly disappointing. Reassuring because our fundamental theory holds up. Disappointing because physicists would love to find something unexpected. Some hint of physics beyond general relativity. Eventually, maybe we will, with more sensitive detectors, more detections, more precise measurements. But for now, Einstein remains undefeated. The ring-down phase reveals the final black hole's properties. After the merger, the new black hole oscillates. These oscillations are called quasi-normal modes. They're determined entirely by the black hole's mass and spin. By measuring the frequencies and damping times of these oscillations from the gravitational wave signal, we can determine the final black hole's mass and spin independently of how we inferred them from the inspiral and merger. This provides a consistency check. Does the final black hole have the mass and spin we expect from combining the original black holes? So far, yes. This confirms our understanding of the merger process, validates general relativity's predictions for how black holes merge, and it demonstrates that the final object is indeed a black hole, not something else. No Hare theorems in general relativity state that black holes are uniquely determined by mass, spin, and charge, nothing else. The ring-down tests this. If the final object had extra structure, extra Hare, the ring-down would differ. We'd see unexpected frequencies or modes, but we don't. The final object behaves exactly like a black hole should. Clean, simple, determined solely by mass and spin. Measuring the Hubble constant using gravitational waves is a tantalizing possibility. The Hubble constant quantifies how fast the universe is expanding. Measuring it precisely is important for cosmology. Standard methods use electromagnetic observations, type Ia supernovae, Cepheid variable stars. These methods give slightly different values. The Hubble tension. Gravitational waves offer an independent method. A standard siren approach. For binary mergers, the gravitational wave signal tells us the distance directly, without needing a cosmic distance ladder. The amplitude of the signal depends on distance. Measure the amplitude and the masses, and you can calculate distance. If you also know the redshift from electromagnetic observations of the host galaxy, you can calculate the Hubble constant. For black hole mergers, identifying the host galaxy is hard. Black holes don't emit light. no obvious electromagnetic counterpart, so we can't easily get redshifts, but neutron star mergers can have electromagnetic counterparts. The one neutron star merger observed with both gravitational waves and light, GW170817, allowed a Hubble constant measurement. The result was consistent with other methods, but with large uncertainties. Future detections, especially with improved detectors that can localize sources better, will improve precision. LISA observations of supermassive black hole mergers, which will be easier to associate with specific galaxies, might provide excellent Hubble constant measurements. This would help resolve the Hubble tension, shed light on cosmology. Black hole mimickers are exist alternatives to black holes. Objects that look like black holes but aren't. Maybe they lack true event horizons. Maybe they're more compact than neutron stars, but not quite black holes. Boson stars, gravastars, other speculative objects. If these exist, their mergers might produce gravitational waves distinguishing them from black holes. Maybe the ring down would differ. Maybe there'd be extra signals, echoes bouncing around inside the object rather than being absorbed by our horizon. LIGO searches for these signatures. So far, no convincing evidence. Everything observed is consistent with black holes as general. Relativity describes them, but the search continues. Ruling out alternatives strengthens our confidence that we're really seeing black holes. And if someday we detect something anomalous, something that doesn't fit, it'll be a major discovery. Evidence for exotic physics. The stochastic gravitational wave background is a faint hum filling the universe, analogous to the cosmic microwave background but for gravitational waves. Countless unresolved black hole mergers, neutron star mergers, and possibly primordial gravitational waves from the early universe, all contributing to a random noise floor. Individual events are too faint or too numerous to separate, but their combined effect creates a background signal. LIGO is searching for this. Advanced LIGO might detect hints. Future detectors will characterize it. Measuring the background tells us about the total merger rate across cosmic history, about the population of sources too distant to detect individually, about possibly exotic sources, early universe phase transitions, cosmic strings, all might contribute. Detecting and analyzing this background opens another window on the universe's history. Precession adds complexity to gravitational wave signals. If a black hole's spin axis isn't aligned with the orbital angular momentum the spin precesses, like a tilted spinning top. This precession affects the gravitational waveform, creates modulations, additional complexity. By detecting these modulations, we measure the precession, learn about the spin orientations. Some observed mergers show evidence of precession. This confirms spin misalignment, supports dynamical formation scenarios where spins are randomly oriented, and it allows precise measurements of the spins and their orientations. Important for understanding formation channels, numerical relativity simulations are essential for interpreting observations. The equations of general relativity describing black hole mergers are too complex to solve analytically. We need computers, massive supercomputers running for weeks or months to simulate a single merger. These simulations provide template waveforms, predictions for what gravitational waves from specific mergers should look like. LIGO compares observed signals to these templates, finds the best match, infers the masses, spins, and other parameters. Without numerical relativity, we couldn't extract detailed information from detections. We'd know something merged, but not what. The development of numerical relativity was a major achievement. For decades, physicists struggled to simulate black hole mergers, instabilities, coordinate singularities, computational challenges. But in 2005, breakthroughs occurred. Multiple groups independently succeeded in simulating complete mergers, calculating the gravitational wave forms. This breakthrough enabled gravitational wave astronomy, made LIGO's detections scientifically useful. Today, numerical relativity simulations are routine. Libraries of waveforms exist, covering wide ranges of masses and spins. These libraries enable rapid analysis. When LIGO detects a signal, within minutes, automated pipelines compare it to templates, identify the likely source parameters, alert astronomers. This rapid response is crucial for multi-messenger follow-up. Electromagnetic follow-up searches happen after every detection. Even though black hole mergers are not expected to produce light, we look anyway, just in case. Telescopes around the world and in space scan the region of sky where the merger occurred, looking for transient sources, new bright objects, anything unusual. Most searches find nothing, as expected, but the effort is worthwhile. If even one black hole merger produced an electromagnetic counterpart, we'd learn immensely. We'd understand the environment, see what's around the black holes, potentially detect exotic physics, mechanisms that could produce light, and the infrastructure built for these searches benefits other science. When LIGO detects neutron star mergers, rapid follow-up is essential. The same networks used for black hole follow-up swing into action. Observe the electromagnetic counterpart. Study the kilonova, the gamma-ray burst, all the light from the merger. This multi-messenger astronomy is powerful, combining gravitational waves with traditional observations, teaching us far more than either alone could. Future detectors will extend our reach. LIGO and Virgo are continuously being upgraded. Improved lasers, better mirrors, more sophisticated isolation from vibrations. Each upgrade increases sensitivity, allows detection of more distant mergers, fainter signals. The planned LIGO upgrades will increase detection rates by factors of several. We'll see mergers across the observable universe, detect black holes forming and merging in the earliest galaxies, watch cosmic history through gravitational waves. Kagura in Japan adds another detector to the network. Better sky localization, more precise parameter estimation. LIGO India, planned for construction, will further improve the network, and next-generation ground-based detectors are being designed. Einstein Telescope in Europe, Cosmic Explorer in the United States. These will be far more sensitive than current LIGO, 10 times more sensitive or better. They'll detect every stellar mass black hole merger in the observable universe. Millions per year. Population statistics will be exquisite. We'll measure the mass distribution precisely, understand formation channels completely, see how merger rates evolve with cosmic time, test general relativity with unprecedented precision. These future detectors will transform gravitational wave astronomy from a new field to a mature science. LISA will observe a completely different part of the gravitational wave spectrum. Low frequencies inaccessible from the ground, seismic noise and gravity, gradient noise limit ground-based detectors to frequencies above about 10 Hz. But space is quiet. LISA, 3 spacecraft in solar orbit forming a triangle millions of kilometers on a side, will detect gravitational waves from millihertz to hertz frequencies. This opens new sources. Supermassive black hole mergers, extreme mass ratio in spirals where stellar mass objects spiral into supermassive black holes, galactic binary white dwarfs, all produce low-frequency gravitational waves LIGO cannot see. LISA will observe thousands of sources continuously, monitor supermassive black hole mergers years before they merge, watch galaxies collide and merge cosmically, see how structure formed, how black holes grew, probe the early universe. LISA is scheduled to launch in the 2030s. When it does, gravitational wave astronomy will expand dramatically. We'll have continuous monitoring of the low-frequency gravitational wave sky, complementing LIGO's observations, together painting a complete picture of the gravitating universe. Pulsar timing arrays provide another window. Millisecond pulsars are incredibly stable clocks. By monitoring many pulsars distributed across the sky, we can detect very low-frequency gravitational waves, nanohertz frequencies, even lower than LISA. These waves would cause correlated timing residuals across pulsars. This technique is sensitive to supermassive black hole binaries at wide separations, years to decades before they merge, and to the stochastic background from all supermassive black hole mergers throughout cosmic history. Recent results from pulsar timing arrays hint at detection, a possible gravitational wave background signal, consistent with expectations from supermassive black hole populations. If confirmed, this is another milestone, another gravitational wave detection method succeeding, showing that the universe is full of gravitational waves at all frequencies. From the rapid chirps of stellar mass mergers detected by LIGO to the slow oscillations from supermassive binaries detected by pulsar timing, all part of the gravitational wave symphony. The implications extend beyond astrophysics. Gravitational wave detections demonstrate general relativity in extreme regimes. They probe quantum gravity indirectly. The horizon area of a black hole is related to its entropy in quantum theories of gravity. Mergers change horizon areas. Do they obey thermodynamic laws? So far, yes. The area always increases. Second law of thermodynamics for black holes. This connects gravity to thermodynamics, to information theory, to quantum mechanics. Deep connections physicists are exploring. Black hole mergers are natural experiments testing these ideas. Hawking radiation, predicted by quantum field theory in curved spacetime, is too weak to detect from astrophysical black holes. But mergers probe related physics. Information paradoxes. What happens to information that falls into a black hole? Does it come out during evaporation? Mergers complicate this. Two black holes merge. Information from both enters. The new horizon. Is it preserved? Can it escape? These are profound questions, not answerable directly from LIGO detections. But the detections motivate theoretical work, push physicists to develop better theories of quantum gravity, to understand black holes at the deepest level. Philosophical implications resonate. Black holes were once theoretical curiosities, solutions to Einstein's equations that seemed too strange to be real. Now we observe them merging. We measure their properties. They're real, common, natural. This progression from mathematical abstraction to detected reality exemplifies physics. Theory predicts, observations confirm, understanding deepens, but it also humbles us. The universe contains objects so extreme they warp space-time into inescapable prisons. Events so violent they release more energy than all the stars in the universe. Scales beyond human experience, beyond intuition. Yet we can understand them, mathematically, observationally. We've decoded nature's most extreme phenomena. That's extraordinary. And it reminds us that the universe is comprehensible, knowable, even in its extremes. Mathematics and physics work everywhere, always, at every scale. The human achievement aspect deserves emphasis. LIGO represents international collaboration. Thousands of people from dozens of countries, scientists, engineers, technicians, students, all working toward a common goal: detecting gravitational waves. This collaboration transcends borders. Politics, differences, united by curiosity, by the drive to understand. When LIGO announced the first detection, people around the world celebrated, not because it benefited any particular nation, but because it expanded human knowledge, showed what we can achieve together. This is science at its best. Collaborative, international, focused on discovery, and it's ongoing. More detectors coming online, more countries joining, more discoveries ahead. This global effort to understand the universe is one of humanity's noblest endeavors. Education and inspiration flow from these discoveries. Students learning about black holes see that physics is alive, active, discovering new things, not a dead body of settled knowledge. This excites young minds, draws them into science. Some will become the next generation of physicists and astronomers. They'll build better detectors, make new discoveries, push knowledge further. And everyone, even those who don't become scientists, benefits from understanding that the universe is knowable, that we can detect space-time ripples from black holes billions of light years away. This perspective enriches life, makes the cosmos feel more real, more accessible, more wondrous. Public outreach has been remarkably successful. LIGO collaborations produce visualizations, animations, sonifications of gravitational waves. The chirp sound is iconic, instantly recognizable. It's been featured in documentaries, news reports, social media. Millions have heard it, understood, At least, basically, what it represents. Two black holes colliding. Space-time ringing. This is science communication done right. Making abstract concepts tangible, accessible, inspiring. And it works. Public support for fundamental science remains strong, partly because people see the value, the wonder, the achievement. Gravitational wave discoveries capture imagination, remind us why we explore, why we invest in understanding nature. The observational strategy for gravitational wave detection requires careful planning. LIGO doesn't run continuously. It operates in observation runs lasting months at a time. Between runs, the detectors shut down for upgrades and maintenance. Each component must be perfect. Mirrors precisely positioned, laser power optimized, seismic isolation calibrated, vacuum maintained. Any imperfection reduces sensitivity, creates noise, masks signals. So the engineering is exquisite. The mirrors are among the smoothest objects ever made. Surface roughness of atoms, suspended by thin fibers to isolate them from ground vibrations. The vacuum system removes air to avoid laser scattering, achieving vacuums better than interstellar space. The lasers are stabilized to incredible precision. Frequency variations of parts per trillion. All of this engineering enables detection. Without it, signals would be lost in noise. The dedication of the engineering teams, often overlooked in favor of the scientists, is essential. They're the ones making sure the detectors work. Day after day, year after year, data analysis presents enormous challenges. LIGO generates terabytes of data continuously. Most is noise, seismic vibrations, thermal fluctuations, laser frequency jitter, scattered light, all creating false signals. Identifying real gravitational waves requires sophisticated algorithms. Matched filtering compares data to template waveforms, looking for patterns that match predictions. Machine learning techniques classify signals, distinguish gravitational waves from glitches. Humans review candidates, verify they're real. This pipeline processes data in real time. When a strong signal appears, alerts go out within minutes. Astronomers scramble to follow up, point telescopes at the sky location, search for counterparts. All of this happens automatically. Software making decisions, humans intervening only when needed, and the false alarm rate must be carefully controlled. We can't claim a detection unless we're sure it's real. Statistical significance must exceed a threshold. 5 sigma. Odds of a false positive less than 1 in a million. Achieving this requires rigorous analysis, multiple checks, independent verification. The collaboration takes this seriously. They don't rush announcements. They wait until they're certain. Waveform modeling continues to improve. Early models were approximate, covered limited parameter ranges. Now, thanks to advances in numerical relativity and analytical approximations, we have waveforms spanning wide ranges of masses, spins, and eccentricities. These models are validated by comparison two simulations, tested against each other. The different models agree where they overlap. This gives confidence. We're not missing physics, not making gross errors, and the models keep improving. Higher order corrections, more accurate treatments of spin effects, better handling of eccentric orbits. Each improvement allows more precise parameter estimation. When we detect a merger, we can say more about it. Measure masses to better precision, constrain spins more tightly, determine distances more accurately. All thanks to better waveforms. The connection to multi-messenger astronomy drives much of the effort. Gravitational waves alone tell us about the merging objects, their masses, spins, distance, but electromagnetic observations would add so much more. The host galaxy, redshift, star formation history, chemical composition, environment, context. For neutron star mergers, we've achieved this. GW Sun 170H17 had a beautiful electromagnetic counterpart. Gamma ray burst, kilonova visible in many wavelengths, radio emission, all telling parts of the story. Combined gravitational and electromagnetic observations taught us more than either alone could. Confirmed that neutron star mergers produce heavy elements, measured the Hubble constant independently, tested theories of matter at nuclear densities. It was a triumph of multi-messenger astronomy. For black hole mergers, we haven't achieved this yet, but we hope to. Maybe some mergers happen in gas-rich environments, active galactic nuclei, accretion disks around supermassive black holes. If so, electromagnetic signatures might emerge. Flares, shock-heated gas, anything detectable. The search continues every time LIGO detects a merger. Sky localization is crucial for electromagnetic follow-up. When LIGO detects a gravitational wave, we need to know where it came from, which part of the sky. Early detections had poor localization, hundreds of square degrees, too large for most telescopes to search thoroughly, but adding more detectors helps. Virgo in Italy joined LIGO. Kagra in Japan is coming online. With 3 or 4 detectors, triangulation becomes possible. The time delay between detectors seeing the signal constrains the direction. More detectors mean better constraints. Future detections with a full network will have sky areas of just a few square degrees. Possibly better. This enables targeted follow-up. Large telescopes can cover that area, search systematically, find counterparts if they exist. This is the promise of the expanding detector network. Not just more detections, but better characterized ones. Compact binary coalescence is the technical term for these mergers, whether black holes or neutron stars. The physics is similar. 2 compact objects spiraling together, gravitational wave emission in spiral, merger, ring down. The equations are the same, only the details differ. Neutron stars have equations of state, internal structure. They can tidally deform. Black holes are simpler. Point masses, no tidal effects. Well, minimal tidal effects near merger, but the gravitational wave signal templates cover both, a unified framework. This allows LIGO to search for all compact binary mergers simultaneously, not just black holes, not just neutron stars, everything, And occasionally we get surprises. Mergers where one object is ambiguous, mass in the uncertain range between neutron stars and black holes. These teach us about the upper limits of neutron star mass, about the transition to black holes, about exotic physics at extreme densities. Cosmological implications are emerging. Gravitational wave observations provide independent distance measurements. No cosmic distance ladder needed. The amplitude of the signal depends on distance. Measure amplitude and intrinsic properties, you get distance. Combine many detections, map the universe's expansion. This is already happening. Each detected merger adds a data point. With hundreds or thousands of detections, we'll measure cosmic expansion history, constrain dark energy, test cosmological models, and we can reach farther than most electromagnetic methods. Gravitational waves are not absorbed by dust, not scattered. They propagate cleanly from source to us. This allows observations at high redshifts into the early universe, where electromagnetic observations are limited. Future detectors will see mergers from the first galaxies. From when the universe was young, this will test cosmology in new regimes, answer questions about structure formation, dark matter, dark energy, inflation, all from gravitational waves. Binary evolution channels are complex. Isolated binaries can evolve through multiple phases. Mass transfer episodes, common envelope evolution, supernova kicks, all affecting the final orbit, whether the stars end up close enough to merge. Some binaries widen during evolution, end up too far apart. They won't merge within the age of the universe. Others tighten, end up in close orbits, guaranteed to merge eventually. Understanding which evolutionary pathways lead to mergers requires detailed stellar evolution models, binary population synthesis codes. These simulate millions of binary stars. Follow their evolution. Count how many merge. When. This provides predictions for merger rates compared to LIGO observations, and the match is reasonably good, within factors of a few. This validates our understanding of binary evolution, shows we're not missing major physics, but refinements continue. Better stellar wind models, improved supernova kick prescriptions, more accurate common envelope treatments. Each improvement brings theory and observation closer. Dense stellar environments like globular clusters are merger factories, thousands of stars packed into small volumes, frequent close encounters, black holes, being heavy, sink to the cluster center, interact with each other, form binaries. Those binaries harden through interactions with other stars. Energy transferred from the binary orbit to passing stars. The binary tightens, eventually becomes tight enough that gravitational waves take over. The merger proceeds. This dynamical formation channel is distinct from isolated binary evolution, and it has observational consequences. Spin misalignment, eccentric orbits, unequal masses, all more common in dynamical formation. LIGO observations show evidence for both channels. Some mergers fit isolated binary predictions. Others suggest dynamical formation. The relative rates are uncertain, but both are important. This means merger sites are diverse: galaxies, globular clusters, open clusters, nuclear star clusters around supermassive black holes, all contributing. Hierarchical mergers are fascinating. A black hole merges, produces a more massive black hole. That black hole remains in a dense environment, interacts with other black holes, forms a new binary, merges again. This can repeat, each generation heavier, eventually producing black holes with masses impossible from single stellar collapse. We've detected candidates for second-generation mergers, black holes with masses around 100 solar masses, spins that suggest they're merger products, not stellar collapse remnants. If these are confirmed as second-generation mergers, it validates the hierarchical scenario, shows that dense environments can build up black hole masses through successive mergers. And it opens questions. How many generations are possible? Can we detect third-generation mergers? What limits the process? Ejections from clusters, runaway kicks, energy loss, all might truncate the hierarchy. But within those limits, hierarchical mergers contribute to the black hole population. Intermediate mass black holes, if they exist, might merge with stellar mass black holes, creating extreme mass ratio in spirals, or EMRI, one small black hole spiraling into a much larger one. For intermediate mass ratios, these are detectable by LIGO, maybe. The waveforms differ from equal mass mergers. More complicated, longer duration, different frequency evolution. LIGO searches for these. So far, no confirmed detections, but hints, candidates that might be intermediate mass black holes. Confirming these would be huge, proving intermediate mass black holes exist, filling the gap between stellar mass and supermassive, understanding their origins, their role in galaxy evolution, all from gravitational wave detections. LISA will excel at extreme mass ratio in spirals, small compact objects spiraling into supermassive black holes. These occur in galactic centers, where stars wander close to the central black hole, get captured, spiral inward over thousands to millions of orbits, all the while emitting gravitational waves. These signals are long, lasting months to years. LISA will observe many simultaneously. From each, will map the space-time around the supermassive black hole. Test the no-hair theorem. Verify the black hole is described by mass and spin alone. Any deviations indicate exotic physics, alternatives to black holes, or quantum gravity effects. LISA will turn supermassive black holes into laboratories for fundamental physics, probing space-time structure at event horizons, testing general relativity in strong field regimes impossible to access otherwise. Gravitational wave memory is a subtle effect. After gravitational waves pass, space-time doesn't return exactly to its original state. There's a permanent displacement, a memory. For black hole mergers, this memory is small, hard to detect with current technology. But next-generation detectors might see it. Detecting memory would confirm another prediction of general relativity, show that space-time can retain permanent changes from passing gravitational waves. It's a beautiful concept, the universe remembering that an event occurred, even after the waves have passed. Eccentric mergers, if detected, will teach us about dynamical formation. Most stellar evolution channels produce circular orbits by the time LIGO detects the signal. But dynamical captures can be eccentric. If two black holes in a dense cluster interact and form a binary, that binary might be eccentric. If they merge before the orbit circularizes, LIGO sees eccentricity. Waveforms from eccentric mergers differ. Multiple harmonics, different frequency evolution. Searching for these requires specialized templates, but it's worth the effort. Eccentric detections would confirm dynamical formation, constrain cluster properties, tell us about black hole interactions in dense environments. Spin precession complicates analysis but adds information. When spins aren't aligned with the orbital plane, they precess. This modulates the gravitational wave signal, creates sidebands in frequency. Detecting these allows measurement of spin magnitudes and orientations. Shows that formation channels producing misaligned spins operate. Some detections show clear precession signatures, others don't. The distribution tells us about formation, about binary evolution, about how black holes end up with the spins they have. High-mass mergers push LIGO's sensitivity limits. Heavy black holes produce gravitational waves at lower frequencies, close to LIGO's lower frequency cut off around 10 Hz. This makes them harder to detect. Less time in the sensitive band. But we're seeing them. Mergers involving black holes of 50, 70, even 100 solar masses. These are interesting because they're unexpected. Standard stellar evolution doesn't easily produce such massive black holes. Low metallicity stars, binary interactions, hierarchical mergers, all might contribute. Each detection adds to the puzzle. Low mass mergers, conversely, are easier to detect in some ways. Lighter black holes produce waves at higher frequencies, spend more time sweeping through LIGO's sensitive band. Hundreds or thousands of cycles detected. This allows precise parameter measurement. But low-mass black holes are quieter, emit less energy, must be closer to be detected. So there's a trade-off. High-mass mergers are loud but brief. Low-mass mergers are longer but quieter. LIGO is sensitive to both, sees the full range from a few solar masses up to hundreds. Population synthesis compares theory to observations. Theoretical models predict merger rate distributions as functions of mass. Spin, redshift, eccentricity, all the parameters. LIGO measures these distributions from detections. Compare prediction to measurement. Adjust models. Improve predictions. Iterate. This process constrains stellar evolution physics, mass transfer efficiency, common envelope outcomes, supernova mechanisms, all uncertain in details. LIGO observations provide empirical constraints, telling us which models work, which don't. Guiding theory. Systematic uncertainties affect interpretation. Waveform models have uncertainties. Parameter estimates have uncertainties. Detector calibration has uncertainties. All must be accounted for. When we quote a black hole mass, there's an error bar, reflecting measurement precision and systematic uncertainties. As detectors improve and models refine, uncertainties shrink. We measure more precisely, constrain better, but uncertainties never vanish completely. This is science. We acknowledge what we don't know, quantify uncertainties, work to reduce them. The community behind gravitational wave astronomy is global and diverse. Scientists from every continent except Antarctica contribute. Though even Antarctic infrastructure helps. Radio telescopes there contribute to pulsar timing arrays. Everyone brings expertise. Experimentalists build detectors. Theorists model waveforms. Data analysts develop algorithms. Astrophysicists interpret results. Educators communicate findings. All essential, all valued. This diversity of skills and backgrounds strengthens the field, makes discoveries possible, enriches understanding. The educational pipeline benefits from gravitational wave discoveries. Students entering physics and astronomy are drawn by recent breakthroughs. LIGO's success inspires, shows that fundamental discoveries still happen, that careers in science lead to real discoveries, not just incremental progress, but paradigm shifts. First, direct detection of gravitational waves. First, observations of black hole mergers, opening a new window on the universe. These are historic achievements. Students want to participate. Enrollment in physics programs increases. Retention improves. Because students see excitement, purpose, meaning. They want to contribute to humanity's understanding, and gravitational wave astronomy provides that opportunity. There are problems to solve, questions to answer, technologies to develop, careers to be made. This pipeline, from undergraduate education through graduate training to professional careers, strengthens science, ensures the next generation continues what this generation started. Public perception of science improves when discoveries captivate. Gravitational waves did that. The announcement made international news. People understood, at least basically, what happened. Two black holes collided. We detected the ripples. This is understandable, concrete, different from abstract particle physics or incomprehensible cosmology. Black holes colliding is visceral, powerful, easy to visualize, even if the details are complex. This accessibility matters. It builds trust, shows that science delivers, that investments in fundamental research yield knowledge, maybe not immediate practical applications, but understanding, insight, beauty, value beyond economics. Societies that appreciate this continue to support science, fund telescopes and detectors, train scientists, pursue knowledge, and everyone benefits, not from gravitational waves directly, but from the technologies developed, the trained minds, the culture of inquiry and evidence, all fostered by scientific research. The unexpected discoveries still to come excite scientists most. We know what we're looking for: black holes, neutron stars, maybe exotic alternatives, but the universe surprises. Every time we develop a new observational technique, we find things we didn't predict. Radio astronomy discovered pulsars. X-ray astronomy found X-ray binaries. Optical astronomy discovered countless phenomena. Gravitational wave astronomy is young. we've barely started. Already we've seen things that challenge models. Black holes heavier than expected, mergers happening at rates higher than early predictions. What else is out there? Maybe primordial black holes, maybe exotic compact objects, maybe signals from cosmic strings or other early universe relics. Maybe something we haven't imagined. This possibility drives the field forward. The promise of surprise, discovery, new physics, new understanding. It's exhilarating. The personal transformation from understanding these concepts is real. When you grasp that space-time is dynamic, that it ripples and waves, that these ripples from black hole mergers travel across the universe and can be detected on Earth, it changes your worldview. You see the universe as interconnected, dynamic, knowable. Mathematical laws govern the most extreme events. We can understand them, predict them, detect them. This demonstrates the power of human intellect, our capacity to comprehend nature, and it humbles. Because the scales involved dwarf human experience. Black holes with tens of solar masses, energies exceeding all stars in the universe, distances of billions of light years, time scales from milliseconds to billions of years. All real, all happening whether we observe or not. We're privileged to live in an era when we can observe, when technology and knowledge have advanced enough that we can detect gravitational waves, can study black hole mergers, can probe the universe in ways our ancestors couldn't imagine. This perspective enriches life, makes the cosmos feel real, immediate, worth understanding. The legacy of this work will endure. Centuries from now, historians of science will mark the 21st century as when gravitational wave astronomy began, when we first detected space-time ripples, when black hole mergers were directly observed. These are milestones, comparable to Galileo's first telescopic observations, to the discovery of the cosmic microwave background, to the detection of the first exoplanet. Each opened new windows on the universe, changed what we know, how we understand. The scientists and engineers working on LIGO and similar projects are contributing to this legacy. Their names might not be remembered individually, but their collective achievement will be. Humanity detected gravitational waves, observed black holes merging, tested general relativity in extreme conditions, all in the early 21st century. And we're just beginning. The detections continue, the technology improves, the discoveries accumulate. Future generations will build on this foundation, develop more sensitive detectors, observe farther, see deeper, understand more completely. This is how science progresses, each generation building on the previous, standing on the shoulders of giants, reaching higher, seeing farther, understanding more deeply. We're part of that chain, contributing our piece, advancing knowledge, leaving it richer than we found it. That's meaningful. That's purpose. That's why this work matters beyond the immediate science. The connection to everyday technology, though indirect, is real. GPS satellites require general relativity corrections, gravitational time dilation, velocity time dilation. Without these, GPS would drift, become inaccurate. The same theory that predicts gravitational waves also predicts these effects. Confirming general relativity through gravitational wave detections validates the theory we use for practical technologies. And technologies developed for LIGO find applications elsewhere. Laser stabilization techniques, vibration isolation methods, ultra-high vacuum technology, precision optics, all developed for gravitational wave detection, all applicable to other fields: materials science, manufacturing, medical imaging, communication. This technology transfer happens continuously. Fundamental research driving innovation, creating tools and techniques that diffuse through the economy, benefiting everyone, not immediately, not directly, but eventually, substantially. Looking forward, the next decades promise revelations, more detections, better measurements, new types of sources, maybe surprises, objects we haven't predicted, signals we don't understand. This is how science progresses. Observations outpace theory. We scramble to explain. Theories improve. New predictions arise. More observations test them. The cycle continues. With gravitational waves, we're early in this cycle. Much remains unknown, but we're learning fast. Each detection adds data, refines models, answers some questions, raises others. This is the scientific process, and it's thrilling. We don't know what we'll find, but we know we'll find something, because the universe is vast, full of phenomena, and we've just started listening to it in gravitational waves. The best is yet to come. Thank you for journeying through the violent and beautiful collision of black holes with me, and remember that these cosmic events, though billions of light years away, teach us about the fundamental nature of spacetime, about the extremes the universe can reach, and about humanity's incredible capacity to detect and understand the ripples in reality itself caused by the most powerful collisions in all of existence.